Let's get a new page. Great. All right, this is day 4, Matlab workshop. Let's set some goals for today. Today we're going to talk a lot about system modeling and simulation. So system modeling and simulation. And we're going to go about this in 3 different ways as long as we have time. I will strive to get all the time we need. First off, we're going to model the system using a transfer function. Then we're going to model the system using state space form. And finally, we're going to model with a good old numerical integration. Oh. So each of these has some pros and cons to it, and some assumptions that have to be made in order for this approach to be appropriate. So let's talk about what those might be. Let's talk transfer functions. What has to be true to write our transfer function? Josh?
I have another question.
Oh, yes.
I was going to ask what the name of the add-on was.
Control Systems Toolbox.
Thank you.
Yep. Anyone want to add? What are some assumptions? Yep, Dylan.
LTI.
LTI, yes, absolutely. And remind me what LTI stands for?
Linear time invariant.
Very good. What else? Initial conditions are 0. Very good. And Jerry said it, single input, single output. Yep, so it has to be LTI, it has to be CISO, and we have to have initial conditions must be 0. Okay. Let's do state space. What's up with state space? What does it have to be? Okay, yeah. Can we do MIMO with a transfer function? Yeah. It just gets hairy, right? It gets a little gross really fast. Okay, so state space is better for MIMO systems. What type of MIMO system? Any MIMO system? LTI. Again, it has to be LTI. It still has to be linear time invariant. Tell me about those initial conditions. Do they have to be 0? Nadal says he doesn't think so, and I agree with him. Initial conditions don't have to be 0. All right, tell me about numerical integration.
Can do nonlinear.
Absolutely.
Time varying.
Yes. Time varying is a little different, but for this class, we're not going to worry about time varying, but yes. Numerical integration, it does not need to be LTI. Doesn't need to be LTI. And it can solve, we can solve any ordinary differential equation. In fact, Matlab, you'll probably have interacted with this at some point before now. Matlab has a built-in function for solving ODEs. What is it called?
ODE 45.
ODE 45. Beautiful. And why is it ODE? Because it's ordinary differential equations. Some people might ask, what is the 45? Well, it turns out there are lots and lots of different options for numerical integration schemes, and 45 denotes one of them. So it's really telling you like some of the details of what's under the hood of that numerical integration function. And 45, ODE 45 just happens to be one that behaves really nicely. It's good for lots of different types of problems, so it's kind of a go-to function. But you might also find there are other ODE number functions available to you, but we'll stick with 45. Yep, Jerry, question?
I was going to ask, is it because it uses the range cutoff method, the run cutoff?
It does use a Runge-Kutta method. Yeah, so if you have taken some numerical schemes before, you might know the term Runge-Kutta. That is one of the types. There are implicit methods, there are explicit methods. They have different orders. Runge-Kutta is just one of them. And so yes, part of that is baked into ODE 45. Okay, great. So we see that probably the most restrictive is the transfer function. Next restrictive is state space modeling, and kind of the free-for-all is numerical integration. All right, so let's hop in and see what each of these looks like. And we're gonna go to one of our canonical toy problems that engineers love to play with, and that is our beloved pendulum. So we will do these three methods, all of them, for the same system, which is our pendulum under gravity. Okay. So we have some ceiling that this pendulum is stuck to. We have some pivot point, and we have some mass that's like a plumb bob out in space, and it's connected with some massless rod that is length L. And this thing is operating under gravity, which we'll call G. And this is a control systems. We're in control systems class. So let's add in something that might control the position of this pendulum. We'll say we have a nice motor that provides a torque at the pivot point. So this is a motor torque. I also need to know, I need to have a way to refer to the state of this system. So let's say that we're going to measure this position through space in terms of a theta that is measured with respect to the vertical. Okay, I have a visual representation of my system. What do I need to do first to maybe go attempt finding a transfer function?
Your equations of motion.
I need to know my differential equations. Yeah. So I first need our differential equations. Okay. Now what you could do is you could sum moments about that pivot point. You could find the rotational inertia of this system given that this mass is an L away from the pivot. You could sum torques due to gravity, torque due to the motor, and you could do the physics for this problem. I'm not going to step too slowly through that. Suffice it to say for today that our differential equation looks like this. All right. I'm hoping that there might be some of you in the audience who see alarm bells going off. I said we want to do a transfer function, and I showed this differential equation. What is the problem?
The sign with the theta t in it.
Yes, the sign is not linear. The variable that I'm curious about is this theta, theta dots, theta double dots, and it's buried within a sine function, so that's not linear. So how am I supposed to do a transfer function when the system has to be LTI and I don't have an LTI system? I can linearize, absolutely. So in some of your other math classes, you might have heard about the Taylor series expansion, which allows you to approximate a nonlinear system as a linear one. It turns out we don't even have to go through all the steps of a Taylor series approximation for this problem. When you do a Taylor series expansion, you have to expand about a what? You have to choose. You have to choose a point, right? So let's maybe draw a visual of this. If I have some nonlinear function, I'm not going to worry about the variables, but it's clearly nonlinear. If I want to approximate this thing as a line, I need to choose which point I'm going to linearize about and find the tangent line at that point. So you need to find the slope at that point, and you need to find the equation of that line. Okay, so we got to choose what we're going to call an operating point. In controls, we usually choose that operating point to be some equilibrium position. Okay, so what do you think might be a good guess for where might be a good place to linearize about for this system?
Theta equals 0.
Theta equals 0 seems easy enough. Let's assume that theta equals 0 is an interesting position that we might be curious about, and let's linearize about that point. And in fact, again, I said we don't even actually have to do the whole linearization. We're going to make what's called a small angle approximation, which means we're going to assume, and again, this is a bold assumption, but we're going to assume that we're going to stay in some pretty close region to 0. Okay, so that means that the angle that goes into this sine function is going to be quite small. So if we choose theta equals 0 as our operating point and make the small angle approximation, we can say that sine of theta is roughly equal to just theta. So let's go ahead and make that small angle approximation. I've got theta double dot equals minus g over L times theta of t plus tau of t over ml squared. Are we good? Any other nonlinearities that I might worry about? Okay, let me put it this way. The variables that I'm concerned with, the theta double dot, the theta, and the tau, are they all multiplied by just a constant coefficient? Yes. That means we're linear, so we're good. So all we had to do was make that small angle approximation. This is, by definition, the small angle approximation, and that made our system linear. Okay? So are we linear? Yep. Now what? Remember my goal? What is my goal? I'm trying to find the transfer function. What's the next step?
Move all your thetas to the other side and your taus on the other, and take the Laplace.
Okay, we could either rearrange and then take the Laplace transform, or we could take the Laplace transform and then rearrange. I tend to do Laplace first. I don't know, maybe I just like Laplace and I jump to it quickly, but either way would be fine. So let's see. I am looking to find the transfer function, which is what over what?
Output over input.
Output over input. And for our system, what is our output? The angle. Yep. So I have some, I'll put it in words first. Over input, what do we as control engineers get to decide on? Torque. The torque. Okay, and remember, once they're in Laplace transform form, they become capital letters. So this is a capital theta, and this is a capital tau. All right, just to set our intentions, we're looking for theta over tau. All right, so let's take that Laplace transform, assuming that the initial conditions are 0. So I need to take the Laplace transform of theta double dot equals Laplace transform of minus g over L theta of t plus tau over ml squared. Laplace transform of theta double dot, what should we get?
Big theta s squared.
Big theta s squared, yes. So the order of the differential is the exponent in the Laplace transform space of s. So I get an s squared because this is a second order differential times big theta of s. I'm going to leave out the dependencies of s because it sometimes starts to look like multiplication and it just gets confusing. Okay, other side, I have minus g over L, which is just a constant. Laplace transform is a linear operator, so we can kind of ignore the fact that it's multiplied by a constant. It's still multiplied by that same constant on the other side of the Laplace transform. And theta of t becomes?
Big theta.
big theta of t. Great. Minus g over L, big theta of s. Sorry, I said t. It's s. All right. Very similar thing happens to tau. It's just multiplied by this constant 1 over ml squared, and this becomes big tau of s. Now we need to do some rearranging, just like Angela said. So we need s squared. Let's put all the theta terms on the left. And we'll keep our tau terms on the right. That is an aggressive T. All right, I'm going to factor out my big theta. All right, so I want theta over tau, so I'm going to have to divide by tau, and then I need to get rid of this stuff, so I'll have to divide by that stuff as well. So what I should get at the end of the day is this. All right, any questions on that so far? No questions, seeing some happy nods. Okay, I'm gonna start to switch over to Matlab now, okay? So finish writing this down because we will need to refer to it when we're working on our Matlab code. I'm gonna switch in 5, 4, 3, 2, 1. Take a picture if you write slow. Okay, cool. All right, so we have our transfer function, and I even showed this on the very first day of class, but we're gonna go over it again. If you don't remember, I like to start out with a clean workspace, so I'm gonna say clear, which clears all the variables out of the workspace, CLC, which cleans up my command window, and if I had any figures open, I would say close all. And I have a scratch code open. Yeah. All right. So does anyone remember from the first day of class what function I use in Matlab to create a transfer function object?
TF.
TF, yeah. It's pretty obvious in Matlab, pretty nice. Okay, let's type in help TF. I don't think that I could program in Matlab if they didn't have the help function because I am always forgetting what needs to go as input to each of the functions. So I typed help TF and I'm scrolling. There's so much documentation on how to use this function. It's super convenient to be able to type help and it tells you exactly how to use that function. So you can see here that it is expecting as the first input a numerator and the second input to be a denominator. That's all well and good, but it actually doesn't tell you, well, it says the numerator coefficients of the transfer function, and it is an ny by nu cell array of row vectors. That's a good bit of jargon. So let's actually make that a little bit more concrete as to what we mean. If I were to have, I'm actually going to pull this up. If I were to have a transfer function If I had a transfer function that looked like this, s squared plus 2s plus 3 over s to the 4th plus 2s cubed plus s plus 9. If I had a transfer function like this, what TF is wanting is an array of the constants that multiply each of the terms of these polynomials. Okay, and it expects them in the order of the highest exponent of s down to the lowest. All right, so for this top one, what it's wanting is something that looks like this. It wants s because 1 because that's what's multiplied by s squared. 2 is multiplied by s, and 3 is our constant. So this is what it wants for the numerator. So tell me what it wants for the denominator.
1, 2,
0,
0.
1, 9.
Good. Why the 0? I don't see a 0 over there.
S squared something.
There's a missing term, right? I could rewrite this as s to the 4th plus 2s cubed plus 0s squared. We're missing an s squared plus s plus 9. Okay? So 1, 2, 0, 1, 9. So this is what it wants for the denominator. Okay, so if we wanted to type this into Matlab, we would say 1, 2, 3, comma, 1, 2, 0, 1, 9. Okay, including those brackets. Okay, what about our pendulum? Our pendulum, we said our transfer function looks like this. 1 over ml squared s squared plus g over l. This is just a constant, and so it's making it a little bit hard for me to tell what are the coefficients of each of these terms. So I'm actually going to rewrite this, bringing that constant into the parentheses. Do we have a missing term in our denominator too?
Yep.
What are we missing? S to the 1, which is s. So I'm going to write 0s plus mgl squared over l. Really, we can cancel an l. We're just left with mgl. Can you guys over here see this okay? Okay. All right. So what do we want in the numerator for our transfer function in MATLAB?
1.
Numerator equals just 1 in brackets, and our denominator is what?
ML squared, 0, ML.
Very good.
G.
ML squared, 0, MGL. Sweet. Okay. So what we need to do is we need to define or set some of those parameters. So the first thing I'm going to do in this code, I'm going to add a comment. Controls, fall 2025, MATLAB workshop 1, 9, 4, 25, Dr. Higgins, and I'm going to give some purpose for what this program is going to do. So we're going to simulate a pendulum under gravity 3 different ways. The same thing that I did before I got started, I'm going to say clear, CLC, close all, just so we always start with a nice clean space. If anyone knows how to turn off, I just updated to 2025. If you know how to turn off these Copilot suggestions, I'd be very grateful because it's annoying me. All right, let's set some of those parameters. We need to set a what? What's the first one you want to set?
Gravity.
M? Oh, gravity? Okay, sure. Let's set gravity equals, we like metric units here. This is meters per second squared. Gravitational constant. Okay, what else? M. I'm going to be super creative here. We'll say we have 1 kilogram. It's a 1 kilogram pendulum. What else are we missing? L. Look at that. It even tries to suggest that I need to define L. Great. I want this to be 1 meter. We're going to make it very simple. Is this font size big enough for everyone?
Yep.
I did try to increase it before class. All right. Let's set a transfer function. I'm going to call this, again, super creative. I'm going to call this transfer function G, T, F. And I need to put in my numerator, looking over here at the board. Numerator is just 1 in brackets. Denominator, M, L squared, comma, 0, comma, m, g, l. Alright. I'm going to hit run. Add to path, yep. Oh good, no errors. And it spits out my transfer function in terms of S down here because I didn't suppress the output. Sweet, we have a transfer function. All right, so we have a transfer function. Does that mean we have simulated our system?
No.
Anyone over here have ideas? What does it mean to simulate?
Could do the step.
Okay, that's one way to simulate a system. What's like the definition of simulating a system? Okay. Simulating your system is just predicting the behavior of the system, and we're going to do it several different ways. But in general, when you hear the word simulation, at least in engineering terms, I want you to think of integrating a differential equation or solving a differential equation. That integration is what allows you to predict the system forward in time. Okay, so notice that I didn't say exactly what input we are going to assume, but we do need to assume some sort of input, right? So we need to tell it, all right, we have this system that has some torque that's being applied. What torque are we going to apply? And I think a great place to start is a step function. So remember, a step function starts out at 0 and it goes up to 1. Here, because we've assumed metric units all the way throughout, that'll be 1 Newton meter of torque at time 0, and we can see what that causes the system to do. All right, so let's do that. In order to simulate your system with a step input, we do step G. Oh man, my fingers hurt. That was so hard. Matlab takes a little while to chew on it. It has some delay, which is not always ideal. But it is going to make our lives very, very easy. Whoa, what's going on here? Is that what you expected to see? Just a block of blue?
It's a step function, right? I mean, if it only jumps up.
So here we're looking at the output of our system as a function of time. So really this is plotting the angle of our pendulum. So how the heck is it just a blue block?
Did we not give it like an input torque or anything to move it?
We did. We said give it a step function.
Okay.
At time 0, give it 1 Newton meter of torque.
Because it's just staying there. No, it's an equilibrium. It's just sitting there.
No? No?
There was a time domain set, so it's just integrating over 10,000 seconds.
That's a lot of seconds. Was that what you were going to say, Mub? Yeah? Okay. You would be correct. Yes, this is a huge amount of time. What's actually happening is we need to zoom in. We need to zoom in and look at a more reasonable period, right? So we would expect a pendulum to do an O word. You said it, Nadal? We expect it to oscillate. Is that what's happening?
Looks like it.
It does indeed look like it. So as I zoom in, it is actually oscillating. And it is possible for us to set the time frame for that step function, and I'll show you that in a second. Notice it's not oscillating about 0. If it were oscillating about 0, that should be the middle of these waves. It's oscillating somewhere higher than that, right? So I'm suddenly applying a constant torque, and so instead of oscillating about 0, it constantly has this torque pushing it up to some angle higher than 0, and it's oscillating forever from there. Okay, why is it able to oscillate for forever? Does that happen in real pendulums?
No air resistance and drag.
Right, we didn't model air resistance, we didn't model drag, we didn't model anything that could zap energy from this system. So this is a very idealized pendulum that will oscillate forever and ever and ever. Okay, let's see what I can do. Let's see if I can press help step and see if I can set that time to be something more reasonable. Okay, it looks like it accepts a second argument t. That's the number of time steps. All right, let's try that. Let's set it equal to like, I don't know, 10. That might be too few. Nope, we're good. 10 seconds shows us that oscillation. Okay, what is my initial position?
The bottom,
Yeah, at time 0, what angle am I at?
0.
0, why is that?
Because you assume initial conditions.
I assumed initial conditions were 0 because I gave it a transfer function, right? Absolutely. Okay. Let's see. Let's say we, instead of applying 1 Newton meters of torque, what if we wanted to apply, 5 Newton meters of torque? So we go from 0 straight up to 5 Newton meters of torque. What do you think would happen?
It's about higher frequency, higher amplitude.
Higher amplitude, yeah. So we could, based on our physics knowledge, know that this is a linear system, and so if we multiply our input by 5, our output is multiplied by 5, so I should expect this amplitude to be 5 times higher. Okay, but I can also have Matlab tell me that by setting the property of the step function that I'm giving it. So this is a little awkward. The way that you set the properties on the step function is you need to create an options object using the resp config function. And if you have a version less than 2023A, this resp config function will not work for you the way it did not work for me last night. Okay, so there is a deprecated version of this for earlier versions, but I would probably recommend just updating. Okay, let's pause this real quick and see what type of object this options thing is. Okay, it says this options is a resp config object with certain properties. One of them is the bias, one of them is the amplitude. A normal unit step function has an amplitude of 1, but I can actually set that amplitude by saying options dot amplitude equals 5. Let's run again. And now when we run again, it says, oh, okay, I'll set that option equal to 5 for you. We'll give a step function of amplitude 5. So now, if I unsuppress my step, that's not what I expected. That's because I needed to tell it to use these options. There we go. 0.2 times 5 is 1. Okay? All right, so we know how to modify our step input. Is step input the only type of input we might be interested in? Of course, says Nadal. No, says I. I think we might want to get fancier things. So we might want to do maybe a ramp function. A ramp function we do with this LSIM. Okay, this LSIM, I can give it my system as a transfer function. Let me see my input signal and my time samples. Let me see if I can find an example, maybe online, of Matlab LSIM to see what the heck does it mean by giving it my input signal, that U. So Matlab has really fantastic documentation. So if you type in help in the function and you're still left with some questions, more often than not, they will have extremely detailed documentation online, and all you need to do is type in Matlab and the function you're curious about, and it should pull up on Google. Okay? So highly recommend utilizing Google to figure out your Matlab questions. Okay? All right, so it's showing here that by system, it says I'm good with being given a transfer function like you've just figured out. And then it's showing you can set the initial, I think you set the initial amplitude and the time steps. No. Yeah, I think you need to hand it that ramp input. Looks like you can give it things other than a ramp input too. So here they're showing generating a square wave as your u comma t, which is your like a trajectory of control inputs. So for every time step you have a u value. You can feed that into LSIM as well. All right. Let's look at a couple of other fun things. All right. I don't believe we've talked about poles and zeros yet. Does anyone want to take a stab at what poles and zeros are? Alex?
Did you say poles?
Poles and zeros.
Poles are when the denominator of a transfer function is 0.
Yep.
Numerator is when they're 0.
Zeros, yes. Okay. So poles are the values of S that make our denominator equal to 0. And we usually do that by factoring our polynomial so that we have a multiplication of terms. Makes it very easy to figure out which values cause it to be 0. And then zeros are in the numerator. The values of S that make the numerator 0. Okay. Let's look back at our pendulum system here. We have a transfer function. Once you have a transfer function, you can find your poles and zeros. We're going to talk about poles and zeros a lot in this class, but we're not going to go into too much detail right now. But if you see content on root locus, you should poles and zeros all day, every day. That's root locus, right? So tell me, do we have any zeros?
No.
No, we don't have any zeros. Do we have any poles?
Yeah, no.
Yeah, what's our pole?
Plus or minus root GL.
Say again?
Plus or minus square root of GL.
Yes, yes. So if this term is 0, everything is 0. So s squared plus g over L equals 0. S squared equals minus g over L. S equals plus or minus the square root of minus g over L. Okay. Which I could rewrite as square root g over L times I or times j. Either one. Matlab is fine with either one. Okay, so it turns out that Matlab has some great options if we want to play around with poles and zeros. I'm going to comment this out. We can do something called PZ map. So let's do help PZ map. What do you think PZ map does?
Pole 0.
It maps our poles and zeros, and it tells us where those poles and zeros are. So we turn in a system, and it spits out the poles and zeros. So let's do that. PZ equals PZ map of G. Okay, we get a 0 real part plus or minus some constant times I. I highly suspect that if we solved out G over L there, we would get something like 3.1321.
Square root of 9 is pretty close.
Absolutely. All right, and we got a Z. I actually was expecting it to spit out a plot, but it didn't.
That's right, plot. Plot, P and Z.
Let me do Matlab plot PZ map. What if I don't assign it to a P and a Z? There we go. Okay, so this is a real axis, an imaginary axis. So for our poles, there's a 0 real part. So our poles are these teeny tiny x values on this 0 real part axis. And then it should have a very small, oh no, and then our imaginary part is plus or minus 3, something. So here and there. Is this a root locus for those of you ahead?
Yeah.
No, it is not. A root locus is when we draw this map for every value of a control parameter that we could possibly choose. Okay, so if we said, all right, I want you to draw my root locus map assuming that I use proportional control. Proportional control means that we get to set that parameter kp. And so the root locus is going to show poles for every value of kp that you could possibly choose. Here, we're not doing that. We're just showing one set of poles and zeros for one choice of kp, which is, I haven't said anything about feedback, so there is no kp. Okay? Pole 0 map. But if you wanted to do the root locus, you could, and that function would be r locus. Whoops. Okay, and that r locus, once your system returns a resulting vector of feedback gains k and corresponding complex root locations r. Let's try it. Let's say okay, so we started out with 0 feedback gain. Here, this is what we had on our regular pole 0 map. And then it said if you include a feedback gain of k, your poles are going to spread apart. Which can be really powerful because it tells you the behavior of your system regardless of which k gain value you choose. So you can look at this root locus to decide what behavior you want to pick out by setting that k value. All right, so root locus is going to be helpful. It is possible that you might know the poles and zeros of your system and not know the transfer function. Now, of course, that'd be pretty easy to figure out, right? Like you just need to do the multiplication on the top and bottom. But Matlab will also do that for you. If you know the poles and zeros and you want the transfer function, you would use ZPK. Whoops, I'm clicking all sorts of places. ZPK. ZPK takes in my zeros, my poles, a gain value that you might set, and it spits out a system the same way that your TF function spits out a system. All right. Okay, so that covers our fun ways that we can play with transfer functions in Matlab. I'm going to switch back to the iPad now and do a few more notes, and we'll talk about state space. State space. Okay, so we have our system. Theta double dot equals minus g over L, theta of t plus tau of t over ml squared. Remind me, what does state space representation look like?
cos b times u vector.
Great. Is that it?
Or,
I heard y.
y equals,
What's it equal?
cy.
Cx plus d, what? U. Very good. Okay. This is my canonical state space representation. And if we remember from our notes previously, there is a process for finding out how to get from this differential equation to our state space representation. So first off, we have to figure out how big is our state space? How many variables do we need for the state? And for that, we needed to know the order, the highest order, and our lowest order for each of the variables. What is the highest order of our theta variable? Great, we have a double derivative. What's the lowest order? 0. We have just the plain function. There's no derivative. What about tau? Is this a d tau dt? 0. Yep, so that's our highest and our lowest. So our state space should be 2 minus 0 plus 0 minus 0, n should be equal to 2. Okay, so I know that x has 2 components to it. And then I need to fill out what are those 2 components. And I know that I take each of my variables and I start from the lowest order up to the second highest order. So my lowest order of theta is what? And the next one is theta dot. Do I write theta double dot? Nope, that's the highest order. I leave it out. What about tau? What's the lowest order of tau? Lowest order is 0, but it's also the highest order, so I don't write the highest order. And I've got my 2 state space values, okay? So we're set here. So this is our state vector. Then I need to somehow mush this into a shape that looks like that. So I need my x dot is the time derivative of each of these items equals some A matrix times my x vector plus my B matrix times my U. All right, so remind me, for that first value here, theta dot is one of my state values. So what does that mean for the top row of A?
0.
It's just, I multiply 0 times theta and 1 times theta dot. Theta dot equals theta dot. We're good on the top. What about the bottom? Do I have an equation for theta double dot? Yeah, that's my differential equation. So I need my bottom row to look like something like this. All right, so that means that I've got to multiply what by theta?
Negative g.
Minus g over L. And then what by theta dot?
0.
Nothing. There's no theta dots up here. There's no theta dots on the right-hand side. But there is something multiplying tau. Is there a tau in the first row of this matrix? No. We said just theta dot equals theta dot. But there is a 1 over ml squared in the bottom. All right. That is our state space representation. I'm not going to switch back to Matlab because it takes too long for it to switch. But the way that we simulate a state space representation in Matlab is crazy easy. What do you think we need to tell Matlab in order to represent our state space system?
AB.
A, B. You like to forget the second equation. C and D. Yeah. So if I want the system in state space representation, I need to tell MATLAB A, B, C, and D. And the function for that is just SS, state space. Okay. And then if I wanted to say, okay, simulate this system for a step function, I just give it G. Again, step G. These are MATLAB codes. I'm going to leave that unsuppressed. Easy, easy peasy. Okay. Questions here?
Do you need to specify steps you like common thing on this one too, or does it not?
Yep. If you wanted it to do a specific amount of time that is not 10,000 time steps, you would need to specify that T final. Yep. And again, you can set the options for the amplitude of that step function just like we did before. Okay, last part I promised was ODE 45. I might have to provide this code offline. ODE 45 does not need to be linear. We just need to write a function that spits out as output x dot and has input is time and x. So what that looks like is in a different file, you'll write function dx equals dynamics. You can really name that function whatever you want, and you need input t and x. So for our system, if we had not linearized about theta equals 0, if we just left the sign in there, this is what dx would look like. I would have, let's maybe initialize dx with some zeros. We'll keep it kind of in that state space representation where there's two equations of motion. And so dx1, the first component of that dx vector, is just my second state. And dx2 is that theta dot equals all the stuff on the right. And we're going to leave it as the sine function this time because ODE 45 can handle it. Sine of my first state variable, which is theta. That can be in a separate file. And then to simulate that system, we need to say ODE 45, tell it to use our dynamics function, and give it some t values, some initial conditions maybe, and we're happy. Okay. All right, so feel free to do help ODE 45 to learn more about ODE 45. Miriam, I was bad and I did nothing to record my screen, but what I'll do is I will type up all of the Matlab functions that I showed you, and I'll comment what each one does, and I will upload that with the notes for today. Okay? All right, well done. Thank you everybody for participating. I'm sorry I'm a minute late. Forgive me. I know, how dare me. Yes. If you're gonna stick around to have more time on the quiz or to do office hours, I'm gonna go up to my office. It's AME 207, and I'm probably gonna go to the bathroom before I go there. Yes, Adonai, thank you. Got it. Thank you so much. Hi.
Can I get my quiz? Because I need to write in one thing and I have a class in 15 minutes, so can I just do that really quick right
Yes.
here?
Yes. Not Sean, no, not Dylan Wood, Dylan Hendry.
Yep.
I will get there, I swear.
It's in there somewhere.
Here, look and make sure I didn't miss it. I'm sorry, I know you have very low time.
It's alright. This will only take a second.
Oh, there it is. Got it.
Thank you.
Thank you. Hi, Miriam.
We can turn in the
Yes, yes. Yeah, let me say that out loud real quick. I'm sorry, I meant to announce this earlier, but because we didn't have normal office hours this week, I am going to allow you to submit homework online up until 6 p.m. tonight. So if you haven't done office hours and you need office hours, I'm doing some office hours throughout today, so email me if you want to join. And then you are always able to either submit on paper or submit on PDF through Canvas. Either one, you don't need to do both, but choose one or the other and you're good. Okay, cool. John, what?
Just a question about the one of the homeworks.
Yes.
It's just like makes a statement and then talks about the platform. There's not, I don't think there's a question.
Yes. You need the full question.
Yeah, and then my textbook doesn't get here until later, so I couldn't just look at the textbook.
I apologize.
You're good.
I took a bad screenshot. Yeah, that's what I was thinking. This is problem, chapter 2 problem,
Yeah.
or chapter 1 problem?
Oh, it's chapter 1.
Okay.
Thank you.
I recently have gotten back into like.
It's after the plane. There it is.
That one?
Oh, yeah.
Yeah, it continues over here, and I totally missed it. Angel, hi.
I have OAS recommendations for
Okay.
doing and stuff.
Yes.
So what can I do for the quiz?
Do you have another class right now? Okay, then come up to my office, and I am going to give you another 15 minutes. to work on
Great.
it.
I mean, I shouldn't need that much, but is that also where the office hours would be?
Yes.
Great. 207?
Yes.
Thank you.
I can move you to somewhere quieter if you
Oh,
need
it's
it.
fine. It's fine.
Okay.
Thank you.
Hi.
2 questions.
Yes.
I have a class, so I can't make office hours. How long are you gonna be doing them?
Probably only an hour, but I have someone else coming in today 4 to 5. Would that potentially work for you?
I don't have anything else to do today, so probably not.
Okay. Can we do that then?
Yeah, I just had a couple questions about the homework. And then,
Okay.
my other question was, did you mark me present the other day when I showed up? Because I got a
Ronald.
notification.
I for sure. You got a notification?
Yeah, that I didn't get marked present for one of my classes, but I only have.
No, I've double checked that I've marked everybody for this course.
Okay.
And you're Ronald, right?
Yeah.
I will double check for you, but I'm like 99% sure that it's not this class that it's an issue for, because I had to double check for someone else too, and I already double checked.
Okay.
Sorry, what's your last name?
White.
Oh, my brain is doing really. Yeah, I have you down for sure every day.
Okay. Alright.
Yes, go up to my office, Amy 207. Melinda, great, thank you. Yeah, I did.
Thank you.
Yep, got it. Thanks. Hi.
My phone died this morning. I just woke up like 30 minutes ago.
Uh-oh.
Is there any way I could take the test for 15 minutes in your office hours?
I haven't let anyone else that came in late for anything other than like a class right before this.
It's okay.
I'm sorry, I just don't think it'd be fair to everyone else that came in late too.
Okay.
I'm sorry.
And then you did
There will
the-
be multiple quizzes though.
And then you did the workshop. Is that like in the book or something?
No, it was a set of notes and Matlab examples,
Okay.
but I will upload the notes, I'll upload the video, I'll upload the Matlab code that we looked at, and I'll comment it. So you should be fine to just catch up on stuff that I upload.
Okay, thank you. Sorry,
You're welcome.
sorry about that.
Remind me your name?
Jacob Shaw.
Jacob. Okay, got it. Thank you, Jacob. Yes.
Did we just that quiz next week, Tuesday? Or is that
I haven't looked that far ahead.
on for next week?
Yeah, I haven't looked that far ahead.
Gotcha. Because I was looking at the schedule.
I'll look.
I saw that because we just had a quiz today, so I thought maybe that was the replacement for next week's quiz or something along those lines. But I don't know if it was anything like that.
Was it quiz 1?
It's it was quiz 1.
Yes, yeah. So that was today.
Okay, so that was today's quiz.
Yes,
Okay,
yeah.
gotcha. So will the schedule stay the same from now on, or is it?
It's always tentative, but I have updated it to reflect what we just did.
Okay.
So you might have an old version.
Okay. And I'll just
Yep.
Thank you.
Yep. Remind me your name? Dylan. Dylan Wood?
For the extra time, we just hang out with you for now.
Yes. We're gonna go up to my office and I will give you extra time.